Hello, everyone. My name is Saeed, and in this part of the talk, I'm just going into more details about ASTRA-sim and how it works and its internal mechanisms. And in later parts, my colleagues will show you some demonstrations of how to run and get some results using ASTRA-sim. So as Tushar said in previous part, ASTRA-sim basically tries to model different layers that are involved in distributed training. And basically, it is based on this observation that when you analyze distributed training stack, what we observed was that on the workload layer and system layer, we don't have too many tools that are modeling these effects in the simulation domain. But on the other hand, we have a lot of open source and detailed network backends. So what we did was that ASTRA-sim captures this workload layer and system layer and has a network API and sits on top of any network simulator that supports that lightweight interface. And we have some default some network backends already integrated into ASTRA-sim repo, that is Garnet and Analytical. But the NS3 backends, although it is done, it is not yet open source, and we have a plan to open source it in next few months, and also another version of the Analytical backend. So yeah, that's the high level overview of what Tushar said. So if you look at here again, this might be just a recall from Tushar's slide, is that we have the workload layer that supports different training loops, and then we have the system layer that basically provides you a rich interface of different communication patterns that you can call from the workload layer. And here you can see that on the network side, we have the Analytical and Garnet, which basically the Analytical backend is very fast and supports various hierarchical topologies like 3D or 2D, 3D based kind of topologies, where in each dimension you can specify the kind of topology that you want to have in that specific dimension. And it is, as I said, it is very fast, but it is accurate for kind of congestion-less communication patterns. So so this means that you only can run topology-aware collectives on top of that, and that the kind of collective algorithms that do not create congestion on that specific topology. For example, one example is just, as Tushar said, a ring. If you have a, let's say, 2D, 3D torus, then if you are running ring-based all-reduced, then it is a very accurate backend to model this kind of network. Then we have Garnet, which models congestion. So it's much more accurate than the Analytical. It supports the credit-based flow control, and its best its most appropriate usage is when you want to model chiplet-based or NUCs, because it also supports those packet formats. And as I said, it's credit-based flow control, which is basically what is most common on chiplet-based and NUCs interconnects. And as I said, because of this network API, you can plug in your own network backends if you want. And the interface is very lightweight, so it is very easy to add and support new network backends. So, okay, so just a very high level detail about the runtime structure of ASTRA-sim is basically when you want to model a system of, let's say, n NPUs, then you create different instances of workload and system layers. And this also, you create different instances of a network API. That network API is actually implemented by the network backend, and then all of those network APIs actually are connected to the network fabric, which all these parts are implemented inside the network backend, and they actually route the traffic and give you a specific and accurate details of the network overheads. So this is the ASTRA-sim directory. Just want to tell you some details, brief details about where each file is. So we have the source files in ASTRA-sim. Then we have some build scripts, how to build it using different backends here. Then we have some examples here, and network backends are maintaining their own repositories and will be cloned as submodules here in extern. And then we have input files for system and workload layer, some sample input files there. And then we have the workload generator that I'll describe later, where you can provide gem operations and give until the prioritization strategy, and it automatically creates creates the workload input file, so that you can just give it to the ASTRA-sim, and ASTRA-sim runs that workload for you. So in this part, I just want to explain the workload layer a bit, and its mechanism. So the code structure inside ASTRA-sim is that inside the ASTRA-sim folder, we have workload system and network frontend, which is basically defining some interfaces with the network backend. But the workload layer exists in the ASTRA-sim/workload folder, and the main file inside that is the workload .cc, where basically you can implement your own training loops. And basically, the training loops, the way that they are implemented there is just using some simple state machines. You can actually model complex training loops. Even complex training loops can be captured using these simple state machines here. And here I just want to give you some example of how, for example, the data parallel state machine is working. And here, suppose you have two NPUs here. So you have some states for going for the forward pass inside the training loop. So you start from init, then you just want to make sure that from the previous iterations, you don't have any pending communication for this layer. So just check that. And once it is done, you just wait for compute times. As I said, the compute times are given to you as an offline parameter by some other external. So here you just wait for that amount of time. And after that, you go again to the next layer. And in the next layer, you again wait. You just check that there is no pending communication for that layer from the previous iteration. And once you confirm that, then you will wait for some certain amount and then go to here. You in this state you wait, and then the next state you will go to the next layer. So you loop through these states until you reach the last layer. And once it is done, then you go to the input grad and wait grad states, which basically you transition to these states here. So here again, you wait for weight gradient computation, and then you go for and then you wait for input gradient computation, and you also then you go to the previous layer, but at the same time you also issue the weight grade communications in the moment that you want to go to the previous layer. And here what happens is that because the nature of the data parallel parallelization strategy, you can issue these communications, and it is not a blocking communication. So you can overlap that with the compute of previous layers. So you can capture all these overlapping scenarios inside the workload layer implementation of ASTRA-sim. And here, and it gives you, and you can accurately model what is happening on optimized strategies. So you do the same thing for all these layers. So you perform these communications once they're weight gradient communications, and in data parallel you only have weight gradient communications. and then go to the previous layer to overlap these communications with compute. So just want to emphasize that this is one way of implementing data parallel. You can decide, I mean, it is all your choice to just decide that, okay, I just want to issue all of the communication at the end. So basically, you just change these state machines a little bit so that you accumulate all of the communications and issue the communications at the end of the back propagation. So all these are all, this is just one sample scenario of how you can, and it is a default implementation of data parallel in ASTRA-sim, but you can change it based on your own needs. So once it is done, then you transition to the forward pass, and then in the forward pass, you want to wait for those communications when you reach each layer. So that this state was for waiting for the communications and make sure that those communications are done. So you issue the communication at one point, then all you do some computations, and then after that, only after that, you wait for those communications to be finished. So that wait actually is a blocking wait, and at that point you want to make sure that the communication is done, so that only after that you are allowed to go to the next iteration. So here is the workload layer input. So each of these three layers have their own inputs for ASTRA-sim, and in workload layer you basically capture the static structure of your workload, basically the compute times and communication sizes and communication types. And here, this is for a sample workload input file for DLRM, where the first line basically you define the training loop, and each of these training loop types have their own implementation inside the workload layer. And then you have some workload specific metadata that workload, that parallelization strategy might need. Then on the next line, you have the number of layers, and here we have 8 layers, and then each following line is just a description, a static description of one layer of the workload. So here is just a layer name. That -1 is just a reserve parameter for later extensions, but these 3 values are forward pass compute, and here the compute times are all in cycles, and by default each cycle is 1 nanosecond in ASTRA-sim, but you can change the cycle duration also is some tunable parameter inside ASTRA-sim, but by default it means here 30 means 300 means 300 nanoseconds, and then you have the forward pass communication type, that is all to all for this embedding layer. Then we have the communication size for forward pass. Then you have the same parameters for input gradient if you have, and here you need to have similar thing for input gradients here. And then you have again similar parameters for weight gradients. So if your weight gradient needs some communications, then you can define communication size and communication types, and also you need to define the compute time for the weight gradient. And here is that if that layer requires a model update, how much does it take? So it's a constant latency that does to take that after the collective communication or any kind of communication is done, how much does it take to just update the model? Which I mean, compared to the actual compute and communication is usually a negligible delay. Oh, yes. Sure.
Is it possible to statically profile embedding operation, which may be highly input dependent?
Okay, so basically you are talking about embedding layers, right? And it's for training samples to training samples that might be different. So basically what you can do is inside the workload layer, when you're waiting for, so you want to account for the compute times of that embedding operation, right? You can give it instead of a fixed delay here, instead of a fixed delay, for example, here, you can change the training loop to wait for a to act like a distribution. For example, just give it a range. So there is a instruction in the workload layer that you say that wait for this amount of time to account for this delay. That delay could be based on a distribution rather than a specific value. So to answer your question, yes, you need to change the workload layer implementation, the training loop.
For every single,
For
every data center, for every data center.
Yes, and my suggestion is that the best way of doing that is just you just pick from it some distribution of the delays for that embedding layer, so that what happens is that if you look at the structure of ASTRA-sim, yes, here. So here each NPU has its own workload instance. So you can you can efficiently implement for that for embedding for this NPU n might take different amount of cycles than NPU 0, for example. And you can do that inside the training loop implementation of the ASTRA-sim.
So what you're saying is that the workload instance does not necessarily need to be static.
Yes, yes, yes. You can capture those things, and if you want, you can basically extend the input file for the workload layer so that so instead of this fixed delay, you can just define some distribution and the parameter of that distribution in the workload input file if you want. You're welcome. Any other question in this part? Okay, so then the middle layer is a system layer which basically tries to model the communication library and all the interactions and system level software that exists on training platforms. And basically, its main file is in sys.cc, and we have two other major subfolders here: the collectives and the topology. And here, it's important to note that collectives work based on some logical topology that they create. For example, ring-based algorithm, collective algorithm works on logical ring, but the logical ring can be mapped to any kind of physical topology. So you can have a switch and you still create a logical ring between these NPUs, or you can have any other physical topology. So it is important to separate these two concepts from each other. So that's why the collective work on the logical topology here. And the physical topology is implemented in the network backend, and that is not shown here. So as I said, each collective algorithm works based on a logical topology, and these topologies are implemented in system.topology, subfolder, and collective are implemented in system.collective. So sorry for this typo here. And the collective algorithms can be implemented again using a state machines. So what does that mean is that just like workload training loop, what is happening is here that again you can implement and add new type of collective communication algorithms again using state machines, similar to training loops that we can implement using a state machines. And here I just want to show you how, for example, a simple ring-based collective all reduced collective can be captured using this simple state machine. So here is that you start from the init, and in the reduced scalar phase, you just transition across these states. So what is happening is that you send some message here, then you receive some message from your neighbor, and you need to wait for the message to be received. And once you receive the message, then you can wait for some arbitrary amount of time to account for reduction with your local data. And after that, then you transition to the next phase of the reduced scalar again. So what is happening is that these sends and receives are actually they are defined by the network API. So the network API provides this interface to you so that you can use it. And any network that sits in the bottom layer actually is responsible for executing the send and receive operations there. So I think the key takeaway of these slides are just you can capture complex interactions using a state machines and then add your own collective communication algorithm to the system layer of ASTRA-sim.
Does it compute node have its own state machine or is it global?
Yes, the system layer is basically replicated across different instances of system layer. So maybe I didn't get your question very correctly. Can you just?
Does this compute node have its own state machine?
Yes. So these are all yes, because you have one instance for each NPU, and that state machine is local to that NPU, and both for the training group and both for the system layer. So this one, yes, each NPU has its own state machines, and they can be in different states according to the network delays and everything. For example, this receive communication might be delivered faster to some NPU so that it can transition faster to the other states compared to the other NPUs, which, for example, due to the network congestion or anything, you have some delays in delivering the message to those receiver NPUs. Okay, so
excuse me, Saeed, I have a question.
Yes.
So I'm wondering how is the NPU model? Could it be given the properties of a GPU or some other accelerator?
Mm-hmm. So that's a very good question. The thing is that you are free to model and get the compute parameters based on any kind of accelerator. So you can either use, for example, you can the thing that here is accelerator specific are mostly compute times. And the compute times are fed as offline parameters to the ASTRA-sim. And you can either use real system measurements like GPU profiling. You can use extra compute simulators, for example, or some other compute simulators like ASTRA-sim, which basically gives you some compute times for any given operation. So to answer you, it's up to you that what you want to model, what type of accelerator here.
Okay, so you mean to say that we can plug in some numbers which we can get from
Yes.
other runs and use it here?
Yes. And this actually provides a nice isolation between the network stack and computer stack. So here you can freely change the compute and the network parameters inside the ASTRA-sim network backend. You can, for example, suppose that you have a GPU. So you want to model GPU, which is in real world is using GPU direct RDMA, for example, in NVIDIA for its communication. But on the ASTRA-sim, if you are using, for example, NS3 backend, you can model this GPU direct RDMA type of communication. And you can decide that, okay, what happens if I use, for example, Ethernet or TCP protocol? And then you also can simulate configurations that do not have real system representations right now. For example, GPU with TCP, what happens if we want to build such a system? So basically, the main usage of ASTRA-sim is just simulating the platforms that do not exist today, and also simulate them at a scale.
Yeah, just to add to what Saeed is saying, I guess not. I hope that works. So just to add to what Saeed is saying, you can, since the compute times come in externally, I think we talk about the workload generation, right, at some point?
Yes.
Yeah, so I think once we come to the workload generation, I think it will be clearer because the work, the compute times come externally, and we have an automated way for doing it with ScaleSim, but you can essentially, do it with any simulator, or you can, as Saeed said, just plug in your own, like you just have to go and modify the workload file and plug in the times that you get externally with whatever simulator. I mean, in the past, we've even thought about officially integrating, let's say, Gen 5 GPU or GPU sim. We didn't end up doing that, but that's like a GPU simulator is something that you can easily run. All you need to do is figure out what compute runs on that GPU, right? So ultimately, depending on the parallelization strategy, you need to decide what is the amount of compute mapped onto that GPU, and then run, whatever simulator or simulation on that GPU to get the compute times, and then feed them to ASTRA-sim. Does that make sense?
Yeah. Yes. Thank you, Saeed and Dr. Tushar.
Thanks. Okay, so yeah, so that's for the reduced scale fields, and then you have some states for doing all gathers again, and again you are using the simple send and receive interface, and also some delays to account for some computations, for example, inside the NPU. So it's again up to you to set these delays here. And this is just a very simple example of how this ring-based or reduce is performed. And then once it is done, then this communication returns back to the workload layer. And if the workload layer pulls this communication, then it is in a done state. So it can proceed further. The workload layer can proceed further if it was waiting for this communication. So we have some internal schedulers at the system layer to just more accurately model the real systems. If you have multiple network dimensions like this, so you basically want to also utilize all of these links at the same time, and you also want to run hierarchical collectives. So, for example, you have 3 network dimensions here. You have packages, then you have rows, and then you have the rows, and then you have columns. So you have 3 network dimensions, and you basically what ASTRA-sim does internally is in the system layer, it creates queues for each of these network dimensions. And what it does is that it breaks these collectives into some chunks. And once you are doing the reduced scatter, when the reduced scatter on the first dimension is done, it goes and will be scheduled on the second queue. And while the reduced scatter of the second chunk is scheduled for on this first dimension. So now the dimension 1 and dimension 2 are both utilized. And you can do this kind of pipelining and concurrency. So ASTRA-sim does this automatically and internally to make sure that you can utilize all of these network dimensions at the same time. On the other hand, you can specify that, okay, I don't want to do that, so that you just have one, you just have the knob to say, okay, how many chunks you want to have. If you just say one chunk I want to have, then you have only one chunk, then that chunk is only being used, is operating on one network dimension. But you have this knob to divide it across multiple chunks, so that you utilize all of these network dimensions at the same time. And this happens. So here I'm just showing you what happens in these network dimensions, and so now this first chunk is completed, and the other chunks are in these queues for their respective stages to be finished. And this way, using this, you want to actually model concurrency and pipelining across different network dimensions. Okay, so any question on these slides so far? And then the system layer itself has its own input format. Then you have scheduling policy of LIFO versus FIFO basically tells you that in the training loop, as you go to the previous layers, you issue newer communication requests. And do you want to prioritize those communications over the previous ones or not? So that depends on the LIFO versus FIFO kind of scheduling policy. Then you can have for each, you can define some certain delays for sending each message to just account for the congestion at the endpoint. How many delays, how many cycles you want to wait for sending a message to any send operations in the communication during the communication operations. Then you have this some again low-level details of pipelining and concurrency, which you can get more details on that on the repository. So I'm not going into too much details of that. Then I think one important detail here is that you have this knob to specify which type of collective communication algorithm you want to run for this topology that you will specify on the network backend. But for each network topology that you want to select, then you will create its respective system layer input to just optimize the way that collective communication or communication patterns operate on that physical topology. And here, basically what it says is that suppose that you have a 3D torus, you basically say that, okay, I want to run all reduce, and on each dimension, because I have 3 dimensions, I have to specify 3 kind of algorithms for each dimension if I'm performing hierarchical kind of collectives. And here I am just specifying that on each dimension, just use the ring-based all reduce. So this way I can tune each communication operation for each physical topology. Okay, so and also you have the knob. So even if you have a multi-dimensional topology, still you can just run not hierarchical, but just one phase kind of reduce, which basically, I mean, you should just give different inputs here, and the details are on the repository. Some examples are there. So basically, this is how you separate the physical topology and the way that you perform communications on that physical topology. And the way that you perform communications is specified on the system layer. The physical topology is on the network backend that you specify. So yeah, I just wanted to highlight this notion of separating these two concepts here. Okay, so now in the bottom most layer, we have the network layer and the network backend, which actually handles its communications and generates some reports. Also, the lowest level reports are generated by the network layer. And we have also reports that are generated by the system layer and workload layer that I will describe later. So each layer has access to some specific details, and based on those details, provide some information and regarding the overheads that you observe on different stacks of the distributed training. So as I said, the network backends are cloned as external submodules that you can find them here on the Excel network backend, analytical, and Garnet. So analytical has the submodule for analytical backend, and Garnet has the submodule for Garnet backend. Then the control flow of the simulation is that the entire main file is always implemented in the network layer, and in the network layer, basically what you do is that on the main file of the network layer, you instantiate different system layers and workload, and the system layer automatically clones its own workload layer. But you instantiate, so the whole flow of creating and connecting all of these pieces together is that in the network layer on the main file, you instantiate the network APIs, you instantiate the system layer, and then you glue them together, and that which basically happens in the constructor of the system layer. And once you glue them together, then you just initiate the workload layer of each instance. And once you do that, it generates events, and the network layer basically needs to process all those events. And once there is no event left, then you know that the simulation is done, and then that's your return. And here is just giving you some details of where these instantiations happen, or on the other hand, where do we create these instances and glue them together. These two are the directories where you can find these instantiations. In the first one is for the analytical backend, the second one is for the garden. So here I just want to give you some high-level comparison between Garnet and analytical. And the main benefits of analytical, as I said, is that it is very easy to define new topologies here. You just, by adding some few lines, you just create a new topology. And then you have a free knob of defining, okay, what is the topology inside each of those dimensions, independent of each other. And then it basically is very fast because it uses a simple link latency bandwidth analytical model to get a latency of this message crossing this link. And as I said, it's accurate when you don't have you tune the communications in a certain way that you know that it doesn't create that much congestion, so that it is accurate for communication patterns that are congestionless. And on the other hand, you have the Garnet, and it's right now you can, by default, you can model the switch-based and torus-based topologies there. The sample topology files are provided in the Garnet backend. But if you want to add new topologies, then you have to write their own topology files. So it requires more work to create new topologies. And as I said, it supports credit-based control flow and does all sorts of packetization, flow control, congestion modeling, and everything. And but the drawback is that it is a slow for if you have a very large scale systems of hundreds or thousands NPUs, then its runtime is slow. And as I said, because it models congestions, it is accurate in all scenarios. If you have congestionless or communication patterns that create congestion, then it works accurate. So these are the two already exist and already open source backends that right now we have inside the ASTRA-sim repository, but we have two more backends that we'll be releasing in next few months. I think the main one is NS3, which basically allows you to simulate RDMA-based and larger scale data center scale distributed training platform. And here I just want to say that the different network backends have their own different format inputs. So this one is the Garnet input format, and the right one is the analytical network input format. So just want to note here that depending on the network backend that you are using, you have different type of formats, input formats. And here, I just want to explain this a little bit more, because here you can see that how easily you can define hierarchical networks on the analytical backend. That you just define that you have 3 dimensions ring. For example, here you want to define a 3D torus. You have ring. Then you can specify in each dimension how many GPUs you have in, or NPUs you have in each dimension. Then how many links you have in each dimensions, the link latency bandwidths, and easily a new topology is created. While in Garnet, the topologies, so here is torus 3D, and we have a switch-based topology. But if you want to use and create other topologies, then first you need to create their own topology input files. It's very similar to the general Garnet, where if you're familiar with Garnet, you need to have a topology file to create a topology first. And the same rules apply here. Okay, so now that we went over some high-level details of these different layers, I just want to show you what is the structure of a typical ASTRA-sim run script. So basically what happens is that you need to specify 3 inputs for that: the network input, the system input, and the workload input. Because you have 3 layers, you want to specify the inputs for each layer. And also because you create binaries with different backend integrations, you also want to determine the, okay, are you using ASTRA-sim with Garnet binary or ASTRA-sim with, for example, analytical backend binary. So you determine the binary file and then different inputs. And then you want to say, okay, where do, after this, where do all these stats should be dumped? And then you specify the directory where the stat files are being stored. And then you have, you just call the binary and give these different paths for different input files for workload, system, and network. And then you also, one important thing is that you also want to determine how many training iterations you want to simulate, and you can specify that here as well. Yeah, so these are some utility inputs for if you have this possibility to run multiple processes and dump all of the processes in the same file, so that all of these files are merged into a single stat file, so that you can compare them very easily together. We have some examples in the example directory where you can refer to for these to use these utility inputs. Okay, so let's go to the reports and what kind of stats does ASTRA-sim report. I think the high-level reports are captured in the end-to-end CSV file that will be generated by ASTRA-sim at the end of the run. And basically, it tells you, and these are the stats that are captured by the workload layer. So workload layer, in the workload layer, the things that you care about is that the total compute times that basically it just accumulates the compute times of different training iterations that and these compute times are already provided to it. It just sums all of them together to just give you this overall compute times that are spent. And all of these delays are in microseconds. Then you have these communication times, the total communication times that are happen for this layer of this DNN workload. And I'll just to emphasize that each of these rows belongs to one layer of the DNN model that you have. So it gives you the layer-wise it gives you the layer-wise overheads for DNN model. And here you see that for weight gradient communications, this is the total amount of time that is spent. And because you don't have any forward pass or back propagation communication, so these are all 0. And the other important metric is that how much of these communications is exposed. Basically, this means that this refers to the amount of communication time where the training loop was forced to stop and you couldn't overlap that communications with compute. So you might have a high communication time here, overall communication time here, but the exposed communication might be less than very much small because you were able to hide it behind the compute. So you can get all of these fine-grained and layer-wise stats here on the end-to-end CSV. And then at the end, this gives you the total compute time and total exposed communication time for the entire, all these layers. So basically this gives you, this is just gives you the overall overheads of the communication versus computation. And all of these things, all of these details are captured on the end-to-end.csv. Okay, so do you have any specific questions on this? I think because this is the main file for reporting the stats and the most useful report file that ASTRA-sim generates. Okay, so let's go into the next, the other important file that ASTRA-sim generates is a detail.csv, which basically most of these reports are gathered by the system layer, which gives you some detailed information of the underlying overheads of the collective communications that are issued for each layer of the DNN model. So here what is happening is that this gives you the queuing delays at the endpoints for each chunks of the collectives. If you remember, we can divide each collective into multiple chunks, and then those chunks will be inserted into a queue. So there might be some delays associated with those chunks waiting for their turn to go into the head of the queue and be processed. So it gives you some, the queuing delays for those collective chunks here. And also it gives you the average message latency for each collective phase. So basically, if you are, for example, if you are executing ring-based all reduce, you break the chunk into multiple messages, and you send each message to, for example, your neighbor, and then receive one message from your neighbor. This basically gives you what is the average latency of that each message that is that has been sent, and what is the latency that the message is received by the receiver for the entire NPU. So this gives you the average message latency for each phase of the collective communication. Okay, so these are very low-level details which you may not it might not be needed for many people. I think the main ones are in the end-to-end CSV that I described in the previous slide. Okay, so using those information, then you can visualize those delays. For example, this one is giving you the overall communication times of different layers of ResNet 50 model. And you see that different layers have a different total communication times. And some of these communications, for example, especially in the last layers, are taking longer. The reason is that, for example, in this specific runs, we use the LIFO scheduling policy, which means that basically once you are going to the previous layers, you want to prioritize those communications of these layers over the communications that is happening to these layers, because those communications are needed sooner. And because of that, you see this overhead of the queuing on the last layers of the ResNet. So you can see the effects that different DNN layers can have on each other. And also it gives you that which layers now are observing highest overheads of the total communications. So this is the overall total communications. You can also get based on the exposed communications, you can get very different stats. Here, for example, what it is showing is that it basically shows the compute times and the exposed communication times for each layer. And here, for example, each layer has some communication overhead, but these communication overheads are hidden behind compute. So you don't see any exposed communication here, because those exposed communications, are fully overlapped with the compute. So this means that they do not have impact on the overall end-to-end chaining. And here only you see this huge exposed communication for the first layer, because, I mean, the reason is obvious, because when you reach here and you issue the communication, you want to immediately go and run the next iteration. But you want the communication of this layer to be finished first. So it is like all of the communication time that is spent on this layer is basically exposed, because you cannot proceed to the next iteration and you are waiting for this communication. So that's how you can get these info, these stats here. And this one is based on the detail.csv, which basically you can get the breakdowns of very fine low-level details of from the collective communications, how much percentage, what percentage is, and what factors are the most dominant. For example, here you see this yellow one is basically giving you the queuing delay for the second phase of the all reviews, which is across. So if you remember the 3D torus, here the second dimension is just rows, which means basically the rows are mostly congested. So the second dimension is now your bottleneck compared to the other network dimensions here. And we have some explanation of why this is happening inside the original ASTRA-sim paper for these studies. All I want to show you here is that you can get like very low level details of what is happening and which specific phases of your algorithm, collective communication algorithm, is becoming the main bottleneck for you. And then you can address and focus on that specific network dimensions if you want to get the most speed up. And using these information, then and those stats that basically enables you to now study the systems at the scale. So here, I think Tushar also showed this figure, which basically tries to see, okay, what happens as we scale the system, and we are using here the VK scaling. So basically, all of the amount of work per NPU remains the same, but because we are scaling the system, the communication overhead is becoming larger and larger because you need to synchronize across more and more NPUs. So you can see that what percentage of the communications is, what percentage of the overall training is because of the exposed communication as you scale the system. So you can then predict what happens. So suppose that you have this system and you want to predict what happens if you scale it more and more. Then you can get these information here. And then you can see, okay, if I want to reduce that using those low level details, you can find out, okay, which aspects of the network or scheduling or anything else I need to address to reduce the communication overhead of these systems. And this one is, again, Tushar explained that, is that it basically, you can now, ASTRA-sim enables you to find out, okay, now what happens if my compute efficiency increases? And here I want to emphasize the reason why you see that the exposed communication ratio increases, although that you're running the same model with the same inputs. But what is happening is that because your compute is now less, you have less compute to overlap the communications with them. And because of that reason, you see that the share of exposed communication also increases. And due to this reason, you can find out, okay, at which point I need to focus more on the network and optimizing the network rather than compute, because anyways, it's just diminishing return, because most of my training iteration is spent on the exposed communication. So there is no point in further improving the compute. Okay, so one of the utility features that we have inside the ASTRA-sim repository is the workload generator, which basically makes it easy for you to define and create new workload input files for new DNN models. And basically what it does is that using that, and it is actually inside the ASTRA-sim scripts workload generator, you can see the README, and there is relatively a detailed README that you can see how to actually use it. Basically what it does is you define the operations in terms of gem operations and MNK sizes, which basically corresponds to this matrix size of inputs and weights. And then you also define the type of parallelization that you want to have for these GEM operations. And here, what is happening is that you are giving it somewhere here. Here you have defined that it's I want to create a workload input file with the data parallel parallelization strategy. And what the workload generator does is that it gets these GEM operations and it splits across the specific dimension that that depends on the type of parallelization that you have, and then it finds the sub operations that each NPU needs to do, and to get the compute times for that, it uses a scale sim. And it automatically finds out what is the communication type and communication size that that you need to have for each layer of that DNN model, depending on the GEM sizes and the parallelization strategy that you have used. And we support multiple parallelization strategies here, like data model, hybrid parallel, and some layer-wise parallelism that you can say that this layer is data parallel, this layer is model parallel, this layer. So you can also define the parallelization strategy layer-wise here. And as I said, for getting the compute times, it gets the, and it internally executes the scale sim. And the scale sim is another simulator that is developed by our lab. And basically it models the systolic arrays and just resembles systems like TPUs. And it has its own inputs again. So you have the knob to go to the workload generator and say that, okay, I want my accelerator to have, for example, 32 MAC units on this axis, 32 MAC units on the other axis, and you can define the SRAM size and everything here. And internal details, you can tune the internal details of your accelerator, and then run the workload generator with this spec, and then it generates the compute times using that specific accelerator that you have described using the ASTRA-sim input file. Yeah, so using that, and then the compute times are gathered using a scale sim. The communication times and communication types are automatically identified by the workload generator, and then you have the workload input file ready for you to just feed it to the ASTRA-sim, and ASTRA-sim will execute that workload input file for you. So yeah, so that was my portion of this talk.